So if you're under the surface where the pressure is, I don't know, 1,000 pascals of gauge pressure, you go twice as deep, you'll get 2,000 pascals of gauge pressure. It doesn't necessarily mean the total pressure doubles because you already started off at 100,000 pascals of baseline from atmospheric. So while going from 1,000 to 2,000 is a doubling, going from 101,000 to 102,000 is not a doubling, right? So you have access to those proportionalities when you're talking about the gauge piece, but not about the total piece. Okay. So that's one application. Let me also do a barometer. You can make a barometer at home. Just take some kind of container of liquid and dump it upside down into another container like this. And the water will actually stick up. And the reason why it sticks up is that you've essentially have the pressure here, which I've been calling what? P2, I guess. That's approximately 0. And so the water here that is above the water line, so to speak, the rest of the water line, it obviously has weight. What is holding it up? Well, it's atmospheric pressure. Atmospheric pressure is all along that height. It's obviously atmospheric pressure here where it's open to the atmosphere. But I should also point out that if you don't increase or decrease your depth, at the same level, you have the same pressure. So basically what's going on here is that the height of the fluid here is how much weight of fluid the atmospheric pressure can support against a vacuum. It's easy to take for granted because atmospheric pressure is all around us. But if you take the pressure down from somewhere else, atmospheric pressure can be surprisingly effective. Another application is a suction cup. All the suction cup does is takes the air out of the inside, and then atmospheric pressure is what holds it on. So I'm just going to use my same formula, P1 equals P2 plus rho GD. Now the pressure at the bottom is atmospheric, and the pressure at the top is basically 0. So if you use a liquid of a given density, and of course your G doesn't usually change, then the atmospheric pressure is proportional to the depth, which means that if the pressure in the atmosphere drops, then the height of the fluid will drop, and if the pressure is slightly larger, it'll rise. So you have a visual representation of what's happening with the air pressure. That can be used to predict weather. That's why I use barometers, and I'll talk about that a little later today or tomorrow. Okay? So you have a visual way to see what is the atmospheric pressure. I guess I should also emphasize, let me write down the equation here, that if you're using a fairly dense liquid, your depth won't be that high. If you plug in normal atmospheric pressure and the density of the liquid, you will get the depth. And when you do this with mercury, you plug in the density of mercury, you will get a height, D, of about 760 millimeters. And so that's why that's an alternative unit for pressure. Instead of calling it atmospheric pressure as in pascals, you can talk about millimeters of mercury, and this is the equation that lets you go from one to the other. So 1 atmosphere, our normal atmospheric pressure, is also called 760 millimeters of mercury. Millimeters of mercury, I think, has more recently been starting to call torr, right? Okay, same thing. The reason they use mercury is, of course, is because mercury is a very dense liquid, and so the height doesn't have to be very big. You could make a water barometer as well, but because the density of water is much smaller, the height of your water barometer would just be prohibitively tall. Okay? Are there any questions on that? Okay, so let's keep going. Same equation, the difference in pressures. So once again, we take a chunk of fluid, it has weight, and yet it doesn't fall down because of the force of the fluid around it. So, what did I say? P1 minus P2 is the force. That's equal to the weight of the fluid. And the next thing I'm going to do is to realize that if I pull an old switcheroo and I grab that water out of there and I put an object in its place that exactly fits that same slot that I pulled the water out of, the surrounding water doesn't know any different. Whatever job it was doing to hold up that water, it's going to do the exact same job on whatever I replace that water with. Okay? So instead of just being the mass of fluid, I'm going to call it the mass of fluid displaced. Okay? So if I take that fluid out, I displace it, and I put something in its place, I still get this same upward force. We often just rebrand this the buoyant force. So this idea is called Archimedes' principle. This was came up with by Archimedes. It's kind of the Newton of his time. This was in BC times, over 1,000 years before Newton. Not a lot of math, not a lot of technology at the time, but just thinking about certain things, you can figure them out. So his reasoning was simply that if you look at fluid, fluid always supports itself. So you can think of it as fluid supports itself. It holds itself up. And so his line of thinking was just, well, if fluid supports itself, it supports anything else in that same space with the same amount of force. And by the way, notice that this argument is more general than even a box shape. I could have some chunk of fluid that's like this with some crazy shape. It doesn't have a clearly defined top and bottom. It doesn't have a clearly defined area of top and bottom. The pressure is trying to get in from all sides with different amounts. And yet Archimedes' principle allows us to realize that if that water doesn't move, it has weight. And if it doesn't, it's because the surrounding water holds it up. And should we now replace that with something else, it may not weigh the same, but the surrounding fluid is going to still continue to do the same job that it did before. Okay? Okay, that's Archimedes' principle. So the amount of force is equal to the weight of fluid you displaced, and I should also mention explicitly that the direction is upward. Okay? This is ultimately just a rebranding of the fact that pressure increases with depth. So the pressure below is always bigger than the pressure above, and so the force that is always upward, straight up, against gravity. So what I'm going to do now is just go through a few permutations of this. We can apply it. Let me go ahead and draw my body of water again. Let me draw my object. Or actually, before I even draw the object, here's my chunk of fluid. My fluid has weight. What we rebrand as the buoyant force is exactly going to hold it up. let me write down my subscripts here. F is fluid. And then I'm going to pull a switcheroo where I grab that chunk of water out and I put in an object in its place, and the surrounding water will continue to do the same job. So whatever lifting force I got from the water before, I get it now. However, just because I swapped out an object of the same size doesn't mean that that object weighs the same. It could weigh differently. So maybe I swapped out the water with like some lead bob or something like that, which has far more weight in the same space. So if it looks like this, and here I'm going to use O for object. So just because the surrounding water would support water in that space doesn't mean it's going to hold up a lead sphere also. So what's going to happen to this thing? It's going to sink, right? It's going to sink because the force you get from the surrounding water is smaller than the weight of this object now. You still get force from the surrounding water, but it's not enough to hold up the object that you replaced that water with. So that's one option that could happen. It'll sink, but it's not going to free fall because it does still have some force, some buoyant force to hold it back. So it's going to accelerate downward, but not as much as if it were out in the air. Let's go back to the original, quickly pull out the water and put in another object of exactly the same shape. The surrounding water does the same job no matter what. But now let's say instead of it's some lead sphere, it's like a styrofoam sphere. And even though it's the same size as the water that it replaced, it actually weighs far less. If that's the case, what will be the motion of the this thing? It'll rise, it'll go upward, eventually float, which we will discuss separately. So you see what we're doing is that in all of these three cases, the surrounding water provides the same amount of buoyant force. The amount of buoyant force we get is basically dependent on how much fluid we've displaced. But we can replace that fluid that we've displaced with an object that weighs more or less than it does. Now, by the way, how is it possible for this to have more mass and more weight than this, even if it's exactly the same size? It's more dense. So this would be for objects that are more dense than the fluid they replaced. Things that are more dense tend to sink. And then over here, of course, how is this weigh so much less when it's the same size as the water it replaced? Well, it's because it's less dense, right? So things that are less dense than the fluid they're in, less dense than the fluid they replaced, will tend to rise instead. Of course, you might ask, well, what about if I replace the water with something that weighs exactly the same amount as it does? Well, then what would happen? It just stays there. So what would be something that has the same density as water? So it would have exactly the same weight as the water replaced. How about some other water? Okay, so if you put water into water, it will not rise or sink. It'll just stay in place because it's just doing the same thing that the original water did, right? So that's just kind of a reaffirmation of the original principle, which is that water supports itself. So if you displace some water and put in some other water, then that gets held up just the same as the original. So as far as calculating for things that don't just stay in place, things that rise or sink, you're going to have one homework problem where I ask you to do this. Essentially, you can just use good old F net equals ma. So you might, for instance, pick one of the directions to be positive. You might say that the buoyant force is positive, the weight of the object is negative, and this, of course, on the right-hand side is the object. So if the two forces on the left-hand side are not equal to each other, they don't cancel each other out, you will have some acceleration. Okay? So that would be an example of how to just fold this right into the stuff that you know from homework 4 and beyond, just Newton's second law. And I'm not going to spoil all the surprises, but you can get an expression for acceleration here where everything else falls out except for the densities. Okay? Now, as far as how to do that, I don't want to give away all your fun, and also I'm about to do something very similar that I don't want to be repetitive with the kind of substitutions that you would want to make here. I also, for full disclosure, there's one force in this equation that is missing, which really should probably be in there, and that's fluid drag. Okay? So there is a type of friction that you experience when you're going through water, and it's obviously huge. This is why if you run through the air, it's really easy. If you try to run through a swimming pool, it's very hard, right? So as soon as something starts moving in a fluid, it's a little silly to propose that there's no fluid drag, right? So there's no fluid drag or fluid friction in this equation. That would be a third force. And so this equation is of limited effectiveness in water, where that drag will be significant. So in the homework problem, it's not a problem of something rising or sinking in water. It's something rising or sinking in air. It's a hot air balloon. Because all of the stuff we've talked about here does apply in air as well. You actually have a buoyant force due to the fact that you're in the air that's around you. Okay? So it's true. So if we go from space, right, where the pressure is none, because we don't have any air up there, we go down, down, down into this ocean of air that coats our planet. The pressure at the top of Mount Everest is going to be relatively low. That's why it's hard to breathe up there. Then we get to the top of my head. The top of my head, the pressure is slightly lower than by the time you get to my feet. So there is a pressure difference from my head to my feet. And that means that the air below has to support the air above. So I do get a slight lifting force from the air around me. It's not much because, of course, when we're talking about how much weight of air am I displacing, that might be like, you know, half a kilogram, which is far, far less, which weighs far, far less than I do. It might lift up like 1% of my body weight or 0.1%, almost nothing. That's why you notice this much more when you jump into a liquid, which is far more dense. When you jump into water, the fluid you're displacing weighs a lot, and therefore the upward force you get is a lot. Okay? So if you want the air to float something, you have to really start getting into an extreme situation. A hot air balloon is massive, right? And it's filled with hot air, which is a little less dense than the cold air around it. It's a little less dense. So the object in that case would be made out of hot air, and the fluid around it would be the cold air. Okay? So what you're trying to do is create enough of a difference between how much that hot air weighs and how much the cold air it displaced weighs, so that you can kind of get in with the deal, the fabric and the strings and the basket and you and your friends. Okay? So if you can create enough of a difference by the difference in hot air and cold air, and that's why those balloons are so massive. Okay? So I have you do this problem where I have you calculate the acceleration of a hot air balloon. Okay? So there, the object is made out of hot air, and the fluid around it is made out of cold air. Okay, so that is a little bit about rising and sinking. And I'd already mentioned that if this rises, it would eventually float. So we should probably take a look at the floating case. That's an important special case. So when something floats, what does that mean? Well, that object still has weight. And yet somehow it's not falling down, it's not rising, it's not sinking, it's just staying in place. And so therefore, the buoyant force that acts on it must be equal to its weight. So that's just so the net force is 0 and we have Newton's first law acting. Okay? This is not Archimedes' principle. This is just simply a statement of if something's going to stay in place, the upward force and downward force have to be equal. That wasn't true over here, right? They are not equal here. In fact, it is the difference between the two that drives the acceleration. It's just that all I'm doing now is setting this to 0, so these two are the same. Because you're not accelerating, these two are the same. I have not yet used Archimedes' principle. Okay? I'm about to use Archimedes' principle by plugging in that the buoyant force that you get from the fluid is always equal to the weight of fluid that you've displaced. So this is always true. The amount of lifting that you get from the fluid is equal to the weight of fluid displaced. Remember, it all comes down from water supporting itself. Therefore, the amount of lifting force you get will be exactly equal to the water that you have displaced. So make sure you understand why this is always true, but this is only equal to this in this case. Okay? And I know it can get very confusing because we have two different weights. One is the weight of fluid displaced, and one is the weight of the object. Buoyant force is always required to be the weight of fluid displaced, but it is only required to be the weight of the object if the object doesn't move. And over here, it certainly does. Okay? So let's go ahead and find out what we have so far. We have both masses involved together, and so this is why it's really important to keep the subscripts there. Keep track of what, when you say mass, what do you mean? Mass of what? I'm going to cancel off the g's. And here, just for visualization's sake, I might as well draw these masses. My mass of my object looks like this. And my mass of my fluid displaced actually is smaller. Okay? Because notice that part of the object sticks up. It doesn't displace any fluid. So the amount of fluid that's been displaced is actually just whatever's below the waterline, right? That's the amount of fluid that had to get out of the way. So these two masses are equal. Equal masses. Why equal masses again? Because they had to have equal weights. Why did they have to have equal weights? Well, because the weight of the object is the downward force and the weight of the fluid displaced is the upward force, and you needed them to cancel to hold it in place. How is it possible if those things are equal mass? They don't look like they're the same size. What has to give? Density, right? So mass is density times volume. Let me plug it in twice. This must be a smaller density because the volume is larger. And this must be a larger density because the volume is smaller. But of course, the product has to be the same because the masses are the same. Okay? So we've just found, with this second line of thinking, that the object has to be less dense than the fluid in order to float, which we already kind of knew from over here, right? We know that this thing had to be less dense than the fluid to rise, and eventually its fate will be to float. Where does it float? Well, right now, it's displacing so much fluid that the buoyant force is larger. So you can think of it as like it pops out of the water, so it gets enough of the object out of the water so that this force is decreased. So this is decreased to just the weight of it. Okay? So instead of the buoyant force being larger than the weight, it throws enough out of the object out of the water, displaces less fluid until the upward force is just equal to its weight. So that's the situation we're looking at here, where we, of course, started from the other end. We started from when something was at rest, these two forces have to be equal. Let me, first of all, point out that these same type of substitutions that I just made, mass is density times volume, Archimedes principle even before that, those are the same types of substitutions that you will need to make over here. So just basically keep that in mind. It's the same kind of things. Let me keep manipulating the equation and we'll get something useful. I'm going to put the volumes on one side and the densities on the other. And you'll see where I'm going with this in just a second. And then as the final step, I'm going to replace the volume of fluid displaced